More teaching materials may be found on the web at astro.unl.edu.
Okay, so what I'm going to talk about today is some science education research that I'm doing at the University of Alaska in collaboration with 6 other universities. And what I'm working on is something that's called research-based science education. When we came up with this 12 years ago, I wish we had thought of a more clever acronym, because RBSE is just a terrible pronunciation. I'm not even sure how to pronounce it. But basically what it is what we're trying to do is give undergraduate non-science majors, so your introductory 101 level students, an authentic science research experience. And the inspiration for it is this, is that when people take a science class, especially at the 100 and 200 level, the primary thing they're doing is they're learning science content. They're learning Newton's laws. They're learning the Krebs cycle, they're learning something chemistry, but what we're doing is we're testing to see how well they know that content. And as a result, students often are left with the conception that being a scientist means you just know a lot of things. And being a good scientist means you've memorized all those books that are on your shelf. They don't know what scientists do because they've never actually seen it and they've never done it themselves. And so what we try to do is we try to give students an opportunity to do a real astronomy research project. And the way we like to think of it is that usually when you do a science class, you teach students the rules of football, but they never actually get to play the game. And what we want them to do is we want students to actually play the game. And in fact, when we do science often, we don't even teach them the rules. We just tell them about great football players and things they did, like Newton, Galileo, people like that. And here, we actually want them to do it. And the goal isn't necessarily that we were going to turn out the next generation of scientists, but we want them to understand what it is that scientists do, and so they can better appreciate it and value it more. So how do we do this? How do we do research in the classroom? Well, again, I said the primary goal is to teach that science is a process. For those of you who are scientists in the audience, I don't know if you've ever had this experience, but whenever I go observing, I often have friends ask me, okay, so you're at the telescope over the week, last week, what did you learn? And I think we're at the telescope, we look through the eyepiece, and then boom, we know the answers, just, you know. And that's how it's shown in every movie, right? You know, that Jodie Foster looks through the eyepiece and, oh my God, that's the answer. So they don't see the process that's involved. We want students to learn that. We also want students to learn critical thinking and project and team-oriented skills, because students often go out and they work in environments where they're working in teams, they're working on projects. Most people's jobs do not involve multiple choice answers, and so we want them to have those sorts of skills to work together. And we also want them to, we want to use our research as a way of improving retention of science content. This is something called contextual learning. And the idea is that if you use something, you tend to retain it because you know it's valuable. And the analogy I like to use is when you buy a DVD player, unless you're exceptional, you don't read the instruction manual from start to finish before you plug the thing in. You plug it in and then you realize you can't get rid of the flashing 12 o'clock. And then you read the manual to actually figure out how to use it. So the idea of contextual learning is students learn science content in the context of doing a research project, and they understand why it's important because they're using it, and that's why they retain it. And so that's one of our inspirations as well. And we also want to improve attitudes for science and science, technology, and education. Science, technology, engineering, mathematics careers, otherwise known as STEM careers. And so even though, so we hope that a lot of these students will want to become scientists or work in STEM careers, and even those who don't will hopefully have better attitudes towards what scientists do and see why it's valuable. So how do we do this? Well, we have these research projects that we've created, and one of the advantages we have in astronomy is there's actually a lot of unanswered questions, because the universe is a big place and there's a lot of things to study, and there's only so many astronomers out there to do it. So there's a lot of questions out there that students can actually make a meaningful contribution. To do this, we have to get them to the point where they can make a meaningful contribution. So we've developed what we call toolbox labs as opposed to cookbook. And the idea is we teach students the skills that they need to know to do the research project. So for example, how to analyze an image to measure the position of a star, how to measure the brightness of a star in an image, how to compare images. And once they have those skills, then they can do the actual research project. And so one of the research projects that we do, which I'll show you in a second, It's called the Nova Search project. And in this project, students learn how to blink aligned images to find stars that are not in one image but in another. And I'll show you an example of that. They learn how to measure the position of the star and also to measure how bright it is. And then we also have them use Excel and other programs to plot the results and to interpret them. And one of the key things that we have our students do is to actually interpret the results. So as a result of doing the research project, what have they actually learned? What do they now know that we didn't know before? And then we have our students do presentations, because any research project is meaningless if you just stick the results in the drawer. If you don't actually present at conferences or publish your work, you've wasted yours and everyone else's time. And one of the key things in the way that we teach it, there's a shift in the teaching style. Rather than the instructor being the one in front who knows everything, the instructor is someone who facilitates the actual doing the research project. So what often happens when I do this type of curriculum with my students is at the end of the project, the students come to me and say, okay, so what was the right answer? Did I get it? Because they're used to being assessed in that way. That they're being assessed on did they find out the thing that I already know. But here what we're doing is we're assessing them on how well they did the process, how well they actually did scientific research. Because we don't know the answer, and I've gotten some pretty funny course evaluations where students have said, this guy's an idiot, he didn't even know the answer to it. Well, yeah, I mean, any research scientist is an idiot, right? Because we don't know the answer to what we're trying to figure out. That's what science is about. So we've developed 6 different research projects that we're doing in astronomy. And for each of these projects, we've created the documentation that the students use to do the research project, but also for instructors so they can figure out what they need to know. We've developed the software and the data sets that they'll use. And then also, as I mentioned before, the toolbox labs. One of the things I'm very proud of is all of the data that we use is real, and it's all from research class telescopes from around the world. And we go through the same process as other research scientists to get time on these telescopes. So it's all real, none of it is fake. So here are the projects that we've developed. And I know that there's many of you are not astronomers. In fact, most of you are not astronomers in this crowd. So what I'm going to do is I'm just going to describe some of these different projects are and how they work. So the first one I'm going to describe is something called Nova Search. And what this project is we're using a telescope at Kitt Peak National Observatory. Kitt Peak is a mountain in southern Arizona. It's about 45 miles west of Tucson. And what we're doing is we're using these telescopes to take pictures of what's called the Andromeda Galaxy. The Andromeda Galaxy is our nearest large galaxy to us. It's often called our sister galaxy because it looks very much what our galaxy looks like. And so what a galaxy is it's a giant collection of stars, dust, and gas. And our galaxy and the Andromeda Galaxy each have about 200 to 400 billion stars in them, depending on who you ask. And so what we do is we look at images of the galaxy, and we take images roughly once a week when we have scheduled observations, which we do right now. And we look to see if we can find new stars in them. So what I'm going to do is I'm going to zoom in here to this red square, and I'm going to show you 2 images of the galaxy. Now one of the things we do is we invert the images because it makes it easier to see. It's like reading, if you remember the early days of the internet, reading white text on a black screen. On a black screen is hard. So what I'd like all of you to do, this is the interactive part, is I'd like you to compare these 2 images and tell me if you can see any stars that are in one image but not in the other. Can you see any? Do you see one?
Bottom left.
Okay, yeah. So do you all see this one right here? Okay, so you can see that there's a star here, but not here. Do you see any others?
Top left.
Oh, yeah.
Okay, yeah. So if you look in the top left here, I can't reach that high, obviously, but you can see in the upper left corner there's a star there, and then there's not one there. So what these stars are, they're stars that are called novae. And what a nova is it's an old star that's called a white dwarf. And a white dwarf is a star that was once like the sun, but it's run out of fuel to burn. It's still white hot, but it has blown off its outer layers, and all that's left is the core of the star. So it's white hot and it's very small. That's why it's called a white dwarf. And white dwarfs are basically like those hot charcoal briquettes at the end of a barbecue. They're still hot, they've burned out all the fuel, and over time they're just going to cool off. Now what a nova is that if that white dwarf star has another star nearby it, that white dwarf's gravity can pull gas off of that companion star, and once enough gas is accumulated, then it will explode as a thermonuclear reaction. And so, sort of like if you have those hot charcoal briquettes and you dump lighter fluid, flare. And what occurs is the star becomes about 1 million times brighter than it was before. So what's happening here is that when we looked at the galaxy in September 3rd, 1995, there was a star that was having an explosion on the surface, and it became bright enough that we could see it all the way in the Andromeda galaxy. But when we looked, 2 years later, that star had faded out. Now the star is actually still there. The star is not destroyed in the explosion, but it's no longer bright enough for us to see. So what students do is they look at these images to find the nova, and then they measure the position of it, and they're also able to measure how bright it is. And if we take observations roughly every week or every month, we can measure how quickly the nova fades out. And there's theoretical predictions about the peak brightness of the nova and how quickly it fades out should depend on the mass of the white dwarf. But the problem is with this research project is not enough nova has been found to accurately test this project. Our students are finding the nova. In fact, one of the things I'm proud of is our research group, which consists entirely of Astro 101 students, have found more novae in the Andromeda galaxy than any other research group ever. That includes Edwin Hubble and others who have studied this galaxy. So we're doing the real thing, and we're actually producing some really impressive results. So here's the arrows, just showing those guys. And I'll just zoom in here to just convince you that this is actually real. So you can see the novas there convincingly in one image. Not the other. Now that's an easy one, but there's a lot fainter ones. And so one of the tricks is with this is taking the time to find them. Now this is a movie right here where we're stepping through a series of images, and if you look closely, you'll see a bunch of novae popping in and out. There's this guy right here that is only one image and then disappears, and you'll see other ones, like there's a guy up here somewhere, and right there, and then it fades out. So some of these novae are called fast novae. They only last for a few weeks to a month, and they may only appear in 1 or 2 images. And others are slow novae that can last for years. And so what the students do is they find them. This is a picture of the software that we use to search for them. In fact, what we use is a program called ImageJ, which is produced by the National Institute of Health. It's a very flexible image processing program, and we've written a plugin which you can use to add functionality. So the students measure the brightness of the nova. This is the one that was found earlier, as mentioned, and we can measure how bright it is in comparison to standard stars. And then this right here is a plot of the brightness of the nova as it decays, and this is the time in days. As you can see, this nova, as it fades out, lasted for almost 300 days. So it was a relatively long nova. And this is a plot of all the different novae that our students have found so far, and we've found over 200 of them inside the galaxy. So there's lots of different projects ideas that students can do, and one of the key things about all of our research projects is that there's a real analysis part of it. So for example, students can look at things like how bright do they get and how quickly do they fade out. And again, is there a relationship between those two as theoretical predictions predict. So for all of our research projects, there is a real analysis part where the students have to think about, well, what does this mean? Okay, yeah, I found a bunch of novae, that's interesting, that's fun and all, but what does it actually mean? What have we discovered as a result of doing this? And that's the part that's essential to it. We get to do other fun things. So for example, these novae, before they explode, they get these hot accretion disks around them, or several million degrees in temperature, so they emit a lot of X-rays. And so I've had students work on projects where they'll compare images of the Andromeda galaxy from the Chandra X-ray telescope and see if any of the novae they have found are in the same position as these X-ray sources. And that's another fun project that students have done. Currently we're doing weekly observations. We're also putting this stuff online, so actually students can do this just by going to our website online. We have a collaborator at Indiana University, Dr. Katie Kolchowski, and this is something she's put on their website, so students can do that there as well. So that's one of the projects. I'm not going to describe all of these in great detail. I just want to show you some of the different examples. Another one we developed recently, which is really a lot of fun, students really enjoy this, is our Killer Asteroids project. And this is a project where students look for asteroids that, what they do are what are called asteroid recovery observations. And the idea is when an asteroid is first discovered, you can get a rough idea of what its orbit is. And you can make a rough prediction as to where it's going to be in the future. But because of errors, large errors in that, as time progresses, you become less and less certain as to where the thing is actually going. So what you need to do are called recovery observations, which is you predict where it's going to be in the future, and then you point your telescope in that direction at that time and see if you actually see it. And so what this is right here is this is an applet that my postdoc created. Actually what he did is he took something from JPL and hacked it to do what we wanted to do. You should always start with something that someone else has done to make it better. And so what this applet does is it allows you to create orbits for different objects. And so we use this to teach students about the orbits of objects. And this is basically the cycle that we go through. So first what we do is students make a prediction as to where it's going to be. And this is called the best guess orbit. And then from that they predict where it'll be. And then we look at it and see if it is actually where it is. It's not always where it's predicted. It's off to the side somewhere. And once you find it again, then you're able to make a better refinement, refine the orbital parameters and predict where it's going to go. So this is an example image of one of our recovery observations. We know which one's the asteroid because it's the thing that's streaking across the sky. That's the easy part. And then you measure where it actually is. And then what you can do is you can use this to better refine the orbit. And so what this plot right here is showing is it's showing an example of one of the asteroids before our students looked at it. And what you're seeing here is this green oval-shaped thing is a bunch of possible orbits for this particular object. And so if you don't know exactly where the object's going, so, for example, some of these orbits might overlap the orbits of planets. And so that's when you get the possibility of an impact. So this is what the uncertainty region was for this object before our students looked at it, and this is what it looked like afterwards. So the students were able to figure out the actual orbit for it, and they were able to calculate that this object was not at risk of hitting any planets. This picture right here shows all the different potential locations of this asteroid beforehand. This is a large portion of the sky. For example, for astronomy buffs, this is the constellation of Leo the Lion. So this is a big portion of the sky. And then after the observations, they figured out that's where it's headed. So they know more precisely where it is. Now for some objects, there actually is a potential for impact. And so what you're seeing right here is a simulation. What the students do is they calculate all these different possible orbits. And what you just saw there was not actually a streak of hundreds of asteroids slanting into Mars. Each one of those dots represents a possibility of which path the asteroid is going to do. So what students can do is they can look at this. I'll show this again. And let's say we calculate 1,000 potential possibilities, and 20 of them actually hit Mars. And what they can do is figure out 20 divided by 1,000, you have a 0.2% chance of this object actually hitting Mars. And this is a fun lab to do for students because all the time this happens where astronomers detect an asteroid and there'll be a small but real possibility it's going to hit the Earth. And then what does the news do with it? And the Time magazine says, oh my God, we're all going to die, we're all going to die. And makes the front page of the news, everyone's really scared. And then they do another set of observations and they realize, no, actually not, we're not going to get, we're fine. And then what do people do? They say, well, what's with these scientists? They don't understand what they're doing. They're a bunch of idiots. You know, first they say we're going to get killed, and then they say we're not going to get killed. What's with these people? Right? And so this is a nice example of the process of science, because science is often about refinement. It's about better, reducing the amount of error and uncertainty in your measurements. And so this is good science. And the fun thing about this project is whenever they realize an object's not going to hit us, they're disappointed. I don't know how to interpret that. I think people will be relieved we're not going to all die, but I guess that's not the So I'm not going to go through all of these. I'm just going to describe some of the other ones. Another thing that we do in our research projects is a study of what's called spectroscopy. Spectroscopy is a study of what kinds of light come from an object. And most of what we know in astronomy is actually from spectroscopy. Spectroscopy is used by astronomers to measure the temperatures of stars, to measure the velocities of things moving away from us. It's used to measure the expansion of the universe. A lot of amazing things are discovered by spectroscopy. And one of the things we're doing with it is we're using it to measure how stars pulsate. And we're studying a class of variable stars that change their brightness and their temperature. So students use observations from this telescope on Kitt Peak, called the Coude-3 telescope. And this squiggly line right here is the plot of the spectrum of the star. Basically what it shows is the intensity of light is a function of wavelength, in other words, color. So this is the blue and violet end of light, and this is getting out to the redder end. And they can use these plots to measure a bunch of different things, including the temperature of the star. We know how far away the star is, and we can measure how bright it is, and once we know the temperature, we can calculate its luminosity and and therefore the size of the star. So we can measure how the star's size is shrinking, expanding and shrinking, and seeing how its temperature is changing with that. We can learn more about what the star is doing. So this plot right here shows how the brightness of some of these variable stars change. They'll be bright for a while, and then the dips down show how it becomes fainter. And so we measure the temperature of the stars as it's bright and as it's faint. And so they download information off the internet to figure out how far away it is. And then using this, they're able to calculate all these different properties. So it's a nice example of how you can take a point of light, something that just looks like a point of light in an image, but using spectroscopy you can learn all these things about what the star is actually doing. Another project that we're doing is students are searching for a rare class of objects called quasars. Quasars are extremely luminous galaxies. We use spectroscopy to do that as well. This is a spectrum of what a quasar looks like. This is a spectrum of a normal galaxy for comparison. And so students look at these spectra and then they calculate what kind of object it is, and determine what kind of object it is, and they're also using a technique called redshift, and using what's known as Hubble's law. They can measure the distance to the galaxy, and they calculate how far away it is. And they are also able to use radio data from the Very Large Array Radio Telescope in New Mexico to measure how big it is in radio waves. So I'm just kind of going through some of the slides. This plot right here is of a website where students put in the data, and it tells them how far away the galaxies are. And this is actually a fun thing to do for students when they realize that something they're looking at is over 10 billion light years away from us. So it's a fun experience. Okay, so what are some of the other projects we do? Another project we do is called photometric redshift. And in this project, what we're doing is we're looking at survey data from that little red square in the upper right corner. And what that's called is the NOAO Deep Wide Field Survey. And what this is a survey to look for the most distant galaxies ever known. And what we're trying to do is, the reason why we're trying to find these very distant galaxies is the further away a galaxy is, the further back in time we're looking. And so the more distant galaxies we're seeing as they look billions of years ago when they were very young. And so by studying these very distant galaxies, we're learning what our galaxy was like a long time ago. And so one of the projects here is to find these very distant galaxies. And so what students do is they look at these images. They download images from the internet. This is an example of what an image looks like in the blue filter in the upper left, the red filter in the upper right, and this is an infrared image in the lower left. And what they do is they use these images to look for objects that are very faint in the blue, but bright in the red and the infrared. These are these very distant galaxies. And then what they do is they calculate the color of the star, and then they are able to, so we load it in our software. They measure the brightness of it, just like we did in the NOVA search. And then these plots right here show what different galaxies will look like depending on what redshift they're at. Redshift here is given by the letter Z. The higher the number, the further away the galaxies are. And so what they can do is they can look and see where the galaxy is on this plot, and then they can tell how far away the galaxy is. And again, the goal of this project is to find the most distant galaxies in the universe. This just shows that same thing we used before. So this plot right here just shows the plots, the distances of different galaxies that our students have discovered. Just showing them on this plot right here. So again, the goal of this curriculum is to see, as a result of having a scientific experience, does it actually improve their understanding of science? So one of the techniques we use to assess this is we have students fill out what are called concept maps. And concept maps are a way to visually represent how well students understand a particular concept. And in this case, the concept we want them to graph out is scientific research. So we ask them to make a graphic map of scientific research. And what we do is we look to see how many of these concepts do they properly understand. That is to say, do they understand that science is a process? It's not just that eureka moment where the light bulb goes off and you know the answer. Do they understand there's many steps involved? Do they understand that research is informed by prior research? For example, many students think that scientific research is you go to the library, or nowadays you go on the internet, and you just read about it. because when they were students, they were told, okay, you're going to do a research project in your history class, so you're going to go read about something. And they think that's what scientists do, but we don't. So do they understand what scientists are doing? That we have questions that are based upon previous research. We use scientific equipment, in the case of astronomy, we use telescopes to collect data. We analyze that data. We usually represent that data in some form, like charts and graphs that are used to interpret it. And then we generate results, and one of the key things we want to find is so they understand that the results generated then influence the next generation of questions, that you're never in a situation where now you know the answer and you're all done and everyone's happy and you can go home. Yet your research now influences the next set of questions the scientists are going to ask. So one of the things we've done is we map to see how well they understand these concepts, and what we're finding is that students on average are making gains where at the start of the class they understand on average 2.8 of these concepts. This is for several hundred students, and by the end of the class students on average have improved to 5.4. Not as good as I would like. And so one of the things we've looked at is to see which areas have they made the most improvement, which areas have they made the least. And the area that they tend to make the most improvement is understanding the science as a process, and as I mentioned before, it generates results that then go back and influence future scientists and science research questions. The areas in which they've made the least gains, in hindsight, are the ones that make the most sense, because what they don't do well in is understanding that science involves data collection. The reason why is in our research projects, they don't actually collect the data. All the data are collected for them using telescopes at Kitt Peak. As much as I'd love to bring all my students down to Kitt Peak, it's just not feasible, especially when you're going from Alaska. So this is a problem we have in our research projects, is students don't actually collect the data. And so not surprisingly, they aren't making significant gains in understanding that part of the scientific research. But it is making improvement gains, and this is what we've been studying for the last few years. And now what we're starting to study is how much does it improve their attitudes towards science. Do they think science is more interesting? Do they think scientists are more interesting? Do they think we're all just a bunch of dweebs, or do they think we're actually real human beings? Would they actually like to do science themselves? And so that's what we're starting to study now. So one of the questions that people often ask me is, well, this sounds like a lot of fun, but I don't really have the time in my class to do this kind of thing, because I have all this science content that I want them to learn. And so one of the things that we like to emphasize is that they learn science content and research as a result of doing this project. So for example, the variable star spectroscopy project, they learn all these concepts. And so if you teach an introductory astronomy class that says anything to do with stars, all of those concepts are ones that you need. And so one of the things that's exciting about it is that these are all subjects that you would talk about in an introductory astronomy class anyway. The students learn it in the context of doing this research project. So it's reinforced as to what's important. So what we're doing right now is we have a partnership with 6 universities. We have a grant from the National Science Foundation, the Education Human Resources Department. We have a collaboration with the University of Washington in Seattle, which actually was a lot of fun, because 2 weeks ago I made an excuse to go to UW to visit them at the same time that my cousin was playing them, and so I got to watch him stomp the tar out of the Huskies. And so we have partnerships. We have partnerships with UW and Indiana University. Our university and Chicago State University are the medium-sized institutions. These institutions are primarily teaching focused. And then we also have 2 community colleges as partners. So what we're looking to do is test these curriculum with these different environments and see how students of different demographics benefit from this research curriculum. So that's what our research is right now. Hopefully in the next few years we'll have more to say. We're also partnering with a new telescope that's being built. It's called the Large Synoptic Survey Telescope, or LSST. And LSST is a giant telescope that's going to be built in Chile, and it's going to do a whole survey of the sky every few weeks, and that'll be our new data source. One of the challenges we have right now is most of our data requires us to go to the telescope and actually observe their manual. But these new telescopes, all the data, all the observations are done automatically. and so you don't need to collect the data yourselves. And so that is the way of the future for our project. So, one of the things that we do, and if there's anyone here at Nebraska who's interested in partnering with us, we are looking for faculty who are interested in using our curriculum. I know there's only so many astronomers here, so I probably look at you and Kevin and maybe yet. But we do have a grant from the NSF which allows us to implement this curriculum at different universities. So if you're interested in using this in your classes, you think this is a benefit for you, we can actually pay for you to do it, which is always a good deal. One thing I'll mention is that our programs work on both Mac and PC, because people always want to know if they work on their computers. So that's something we have to do. So one of the things that we do, if you're interested in doing this, is that we have these assessment tools that we use, and these are the assessment tools we use to see whether or not students are benefiting. My background is in astrophysical research, and I'm learning that science education research is actually a lot harder because it's quite challenging to understand the minds of our students. There's no computer program that can simulate that. So if you're interested in learning more about our projects, I'll just leave this as our final slide. This is the website, and we have information listed on this website. We have all of our research projects information listed there. I do not know why my former postdoc decided to name the computer Uranus. That just seems a bad idea. That's the name of the machine that has material on it. So if you're interested, more interested in that, you can check that out. Another thing I'll mention, one of the things we also have on here is we have a thing on making color images. Tomorrow night I'm giving a talk on how we make color astronomical images. That's something that we do with students. So I'll stop with that. If you have any questions, I'll be happy to answer them.